Okay, so that is up and running. Let me share my screen. So. Simon. Okay, so where did we stop the last time? We were here. Did we do 7? No? Yes, ma'am.
We were told we could go up to question 7, but we didn't do it in class.
Oh, okay. So we did the others. We did 6 and 5 and so on, right?
Not as a class, but not as a kid.
All right, let me see here. I think I remember doing this one.
Yeah, we did. Yeah.
Okay, all right, I do remember doing that one. Did we do 3?
Not together.
All right, let's do 3. So 3 says, what is the pressure of a gas if you compress the gas from its original 500 mil at 3.44 to a volume of 302 mils? Okay, so my question to you is, what law comes into mind when it comes to this question? Yes, ma'am.
Well, it's called, but I, the formula is gonna be P1, V1, equals P2, V.
Yeah, that's Moore's law. P1, V1 is equal to P2, V2, right? So I think I made the point that when I was going through some examples in the PowerPoint, I made a point that when you're faced with a question like this, you have to identify, what the different terms are, P1, V1, and so on, right? So what would be P1 in this particular case?
3.41.
Exactly. What would be V1 in this question?
500.
The 500 mils. And what would be V2? And the question is asking for P2, right? So we have to rearrange this equation to get P2 is equal to P1, V1 over V2. So we just put the numbers in. P1 is 3.42 times V1, which is 500 mils, all divided by V2, which is 302 mils. All right. So let's see what this is. 3.4 times 500 and then divided by 302. So according to my calculations, rounded off to 2 sig figs, this would be equal to 5.6, and the units here would be torr because the milliliter units would cancel out. All right, and that's how that is done. I don't remember if I told you this. Whenever it comes to using the Moore's law, it doesn't matter what the pressure units are, and it doesn't matter what the volume units are, as long as they're the same on both sides, right? So the units for P1 and P2 has to be the same. Units for V1 and V2 has to be the same. All right. Okay. Any questions about this one? Any questions? Any questions? And that includes you guys out there at Zoom. If you have any questions, feel free to chip in. Any questions? Questions? All right. Let me clear this and scroll down to number 4. So number 4 says, at what temperature will a gas be at if you allow it to expand from an original 456 mils at 65 degrees Celsius to 3.4 liters? Okay, so which law comes into mind in this particular case?
Charles.
Which is
B1 over T1 equals
V1 over T1 is equal to?
B2 over T2.
Okay, very good. So we have to identify these as different terms in the question. So what is V1?
156 mil.
Okay, so that's V1. What is T1? Okay, or remember, when it comes to temperatures in any of these laws, what do we need to do if it's in Celsius? Convert to Kelvin, so that would be 65 plus 273, so 338 according to my calculations would be the value expressed in Kelvin. All right, and then what is V2? 3.4 liter, all right? And the question is asking for T2, right? So how would you arrange this to get T2?
T2 equals V2 times T1,
V2 times
T1,
T1 over
V1.
V1, exactly. So we put the numbers in. Now for V2 is 3.4 liters, right? Times T1, which is 338 Kelvin, divided by V1, which is 456 liters. But here we have a situation where V2 is in liters and V1 is in milliliters. So what do we need to do? We have to?
Convert it.
All right, so you can convert either the liter value to milliliter value or vice versa. It doesn't really matter. So what I'm gonna do is convert milliliters to liters. So down here, I'm gonna put 1000 mils. And up here, I'm gonna put 1 liter. And that's the setup, so it would be 3.4 times 338. And then divide that by 456. Whoops, 456. Divide by 1000. And you need to round this off to 2 sig figs. So when you round off the 2 sig figs, I got 2500 Kelvin, right? The question did not specify what units the temperature must be expressed, so you can leave it like this. Or if you want to convert Celsius, that's fine by me. But that's basically it as far as this question is concerned, all right? Okay, any question about this one? Any questions about number 4? Any questions? No questions? All right. I take it that you have a complete understanding of number 4, so let me clear this. And scroll down to number 5. So number 5 says, if you have 0.56 moles of an ideal gas at 87 degrees Celsius and a pressure of 569 torr, what volume will the gas take up? So what equation comes to mind in this particular question? What equation comes to mind in this particular question? They gave you the moles, they gave you the temperature, they gave you the pressure, and the question is asking for the volume.
PV.
PV is equal to nRT, right? So PV is equal to nRT. Okay, so what's a P in this question? So this is the P, all right? What is the V? We don't know because that's what the question is asking for, right? Okay, so what is the N? Yes, ma'am. Okay, so that's the N. And R, of course, is always a constant, 0.0821 liters atmospheres over mole Kelvin. That does not change, all right? And then the temperature. What's the temperature? The 87 degrees, right? But we have to convert that to Kelvin. So 87 plus 273. So that's 360, the decimal point, Kelvin. All right. So the question is asking for V. So based on this equation, what is V going to be equal to? If we rearrange this equation to solve for V, V will be equal to what?
nRT over P.
nRT over P. And all we have to do from here is plug the numbers in. So for N, that's 0.56 moles times R, which is 0.0821 liters atmospheres over mole Kelvin, multiplied by the temperature, which is 360 Kelvin, and then we divide all of that by the pressure, which is 569 torr. But guess what? We have atmosphere units here and torr units here. So what do we need to do? we convert the torr value into atmosphere. So how do we do that? What do we multiply that by in order to convert from torr to atmospheres?
1 atmosphere over.
1 atmosphere above, 760 torr below, right? So, in terms of the cancellation of units, the moles will cancel here and here, Kelvin will cancel here and here, torr will cancel out here and here, atmospheres will cancel out here and here. So whatever you get in your final answer, unit is going to be liters. So let's do this calculation here, 0.56 times 0.0821 times 360 divided by 569 times, or divided by 760. Okay, so according to my calculation, I got, let me say fix, 2 fix, okay. I got 22 liters. All right. So please check to make sure I'm doing the right thing, but I think that answer is correct. All right. Any questions about this one? Any questions? Any questions? Nope. Number 6 says you have a gas at 453 millimeters mercury with a volume of 700 mils and a temperature of 25 degrees Celsius. What will the temperature of the gas be if you change the pressure to 278 millimeters mercury? It should be mercury here. Okay, so what law comes to mind in this case? They gave you the initial pressure, they gave you the initial volume, they gave you the initial temperature, and then they're asking for the final temperature, and they gave you the second pressure. So what law comes to mind in this case? Yes, ma'am. Okay, the combined gas law, which is P1 V1 over T1 is equal to P2 V2 over T2. That's the combined gas law, right? So, okay, so let's identify the different terms. Let's start off with P1. What is P1 in this case? Before 53 millimeters mercury, okay? What would be the V1 in this case? Okay, so the V1 is the 700 mils. And then what would be the T1? What would be the T1? Right, the 25, which you have to convert to Kelvin. So T1 would be 298 Kelvin. All right, very good. Now the question is asking, what will the temperature be if you change the pressure to 278, right? So what the question is asking for is T2, right? And the question gave you the second pressure, which is 278, so that would be P2. So what that tells me is that basically the temperature doesn't change, right? The pressure will change, right? Because the initial pressure is P1, the final pressure is 278, which is P2. The volume will change. Oh, my bad, I misspoke. It's a volume that won't change, right? The temperature changes from the initial temperature, which is 298 Kelvin, to what the question is asking for. So basically, we can simplify this equation because V1 is equal to V2, right? So therefore, these two will cancel out. So basically, you're going to end up with P1 over T1 is equal to P2 over T2. So based on that, what would be the equation for T2?
P2 T1.
I'm sorry, repeat that?
P2 T1 over P1.
P2 what?
T1
T1 over?
P1.
Okay, very good, right. So basically, all we have to do now is put the numbers in. P2 is 278 millimeters mercury times T1, which is 298 Kelvin, all divided by P1, which is 453 millimeters mercury. So let's see what this gives. 278 times 298, and then I divide that by 453. So according to my calculation, rounded off to three sig figs, this would be equal to 183, and the units here would be Kelvin. That's how that is done. All right? Any questions about this? Any questions? Any questions? Any questions? Okay. Let me clear this. Let's go down. Okay, perform the following calculations. And the first one is to find the density of sulfur trioxide at 0.96 atmospheres and 35 degrees Celsius. So what equation comes to mind for this question? There's a question that there's an equation that you can use to calculate the density. We derived it, right? What's that equation? Yes, ma'am. I'm sorry?
Mass over volume.
No, well, that's true, but there's another equation. I should have been more specific. That's true, right? But the equation I'm looking for is one that applies to gases. There's one that we derived in class. Density is equal to MP over RT. And just to remind you of what these terms are, M is the molar mass, uppercase M, right? That's the molar mass. P is the pressure, R is of course the molar gas constant, and T is the temperature in Kelvin, right? So let's apply this to solving this question. So what's the molar mass of SO3? Well, you know me, you know how lazy I am. I'm going to go to my molar mass calculator, which unfortunately you guys won't have access to during your tests. So that sucks for you guys. Let's see here, molar mass of SO3. So that is equal to 80.06 grams per mole. All right. So 80, whoops. 80.06 grams per mole multiplied by the pressure. What's the pressure? 0.96 atmospheres divided by R, which is always 0.0821 liters atmospheres over mole Kelvin, multiplied by the temperature, which is 35 degrees, which you have to convert to Kelvin. So that's what? 35 plus 273. So that's 308 Kelvin. And then we do the number crunching. So 80.06 times 0.96. And then divide that by 0.0821. 08. So according to my calculation, I think I did something wrong. I'll do this. 80.06 times 0.96 divided by 0.0821 times 808. Okay, this looks more like it. So the answer I got, and many sig figs, 2 sig figs. So that would be 3.0. And the units would be, well, let's do the cancellation of units. ATM will cancel there. Kelvin will cancel there. Mole will cancel here. So the units for density in this case is grams per liter. And that's how that is done. All right, any questions about this one? Any questions? Any questions? Okay. In the case of B, they're asking for the same thing, but they're stipulating that the conditions are STP conditions, right? So you all remember what STP means, right? Standard temperature and pressure, where the temperature is 273 Kelvin and the pressure is equal to 1.00 atmospheres, right? So we could use the same equation here, but use T equals to 273 and P equal 1 atmosphere. The molar mass will still be the same, and of course R will still be the same. So you could put the numbers in here and get the answer, right? But believe it or not, there's a much easier way to do this problem. I wonder if anybody can tell me what that easier way would be. And it's kind of related to what she said before in terms of the definition of density, mass over volume. There's an easier way. I mean, you could do it this way, you'll get the same answer, but there's an easier way of doing this problem. Let me give you a hint. Do you remember what the term molar volume means? Molar volume. What does molar volume mean? And you guys out there in Zoom, you can chip in as well. What does the term molar volume mean? Yes, ma'am.
The volume occupied by one mole of.
Exactly. The volume occupied by 1 mole of a gas, right? So we have a molar mass. This is the molar mass right here, which is a mass occupied by 1 mole of a gas. And the molar volume is the volume occupied by 1 mole of a gas. So my next question is, what is the volume occupied by 1 mole of gas under STP conditions? Yes, ma'am. Exactly, right? So basically, we can calculate the density as being equal to the mass, the molar mass, which is 80.06 grams per mole, divided by the molar volume, which is, as she just told us, 22.4 liters per mole. And that's it, right? So as you can see, that's much easier than using the equation that we use for question 7a. So all we have to do now is divide 80.06 by 22.4. And according to my calculation, this works out to be equal to 3.57. And the units here again would be grams per liter, right? So that's a much easier and shorter way of doing this problem. Okay, any questions about that one? Any questions? Any questions? Any questions? Okay, let me clear this. Okay, and scroll down to the letter C. In this case, they're asking for the molar mass of a gas if its density is 3.67 grams per liter at 15 degrees Celsius and 825 torr. Now, okay, well, let me ask you this. What equation comes to mind in order to solve this particular problem? They gave you the density, the temperature, and the pressure, and the question is asking for the molar mass. So what equation comes to mind? What equation relates the molar mass, the density, the temperature, and to pressure? Exactly, the same equation we used in the previous problem. Density is equal to MP over RT. This time, the question is asking for M, right? So what would M be equal to based on this equation? If we were to rearrange this equation to solve for M, what would M be equal?
To
Mm-hmm.
DRT
Mm-hmm. Over P, exactly. So the D is 3.67 grams per liter, multiplied by the R, which is 0.0821 liters, atmospheres over mole Kelvin, multiplied by the temperature, which is 15 degrees, which we have to convert to Kelvin, so that's 15 plus 273. So that gives 288 Kelvin. And then we divide by P, which is 825 torr. But again, we have a situation where we have the torr units here, we have the atmosphere units up here. So again, we have to convert from torr to atmospheres. So 1 atmosphere will be equal to 760 torr. And that's the setup, so let's do the calculation. 3.67 times 0.0821 times 288, and then divided by 825, divided by 760. And according to my calculation, now we have to round up to 3 sig figs. So according to my calculation, that would be 79.9, and the units here would be, well, let's see here. The liter units will cancel out here and here, atmospheres cancel out here, Kelvin cancel out there, the torrs cancel out there and there. So the only unit remaining would be grams per mole. So that would be the unit of molar mass in this case. All right? Any questions about this one? Any questions? Any questions? Okay, let's see here. In the case of B, in this case, they're asking for the same thing, the molar mass, right? They gave you the mass, they gave you the volume, they gave you the pressure, and they gave you the temperature. So which equation would you use to get the molar mass in this case? You could use this equation here, or actually you could use this equation here. But there's a slight difference, and the difference is that they did not give you the density in this question. However, they gave you the means by which you can calculate the density, because they gave you the mass and they gave you the volume, right? So the mass divided by the volume would give you the density, and then you can do the rest of the calculation. So let's do that. So the density would be 4.40 grams divided by 3.50 liters. And then we multiply by 0.0821 liters atmospheres over mole Kelvin times the temperature. What's the temperature? 41 degrees. So 41 plus 273. 314 Kelvin would be the answer for that part. And then we divide by P. And what is P? 560 torr, which again we have to convert to atmospheres. 760 torr. So that would be the setup right there. So let's see the result of this. 4.4 divided by 3.5, and then I multiply by 0.0821, and then I multiply by 314, and then I divide by 560 times, or not times, divided by 760. And according to my calculation, now, how many sig figs do I need to go? Okay, 2 sig figs because of this right here. So my calculation says the answer is 44 grams per mole. All right? So that's basically how that is done. Any questions about this one? Questions? Okay, so let me clear this. Let's go down. Okay, so this question is dealing with a mixture of gases, right? And it gives you the masses of each gas, and it gives you the temperature, and it gives you the volume. And the question is asking for you to calculate the partial pressure of each gas. All right? So basically, all you have to do is use the ideal gas equation. Or, hold on, let me see here. You could use the ideal gas equation, or I think this is a more convenient way of doing it. I don't know if you guys remember this equation. M is equal to lowercase mRT over PV. Remember that equation? Right, I gave you, well, we derived this, right? We can use this to determine the molar mass of a gas, right? What we can do is rearrange this to get an expression for P. So that would be equal to mass in grams times RT over the molar mass of the gas times V. All right? So basically, we use this equation to calculate the pressure of each gas, the nitrogen, the hydrogen, and the ammonia. So let me start off with the nitrogen. The mass of the nitrogen given in the question is 3.50 grams multiplied by 0.0821 liters atmospheres over mole Kelvin, excuse me, times the temperature. What's the temperature? 25 degrees Celsius, which is 298 Kelvin, right? And then I will divide that by the molar mass. Now for nitrogen, 14.01 times 2, so that would be 28.02 grams per mole. And then I multiply that by the volume, which is 1 liter, because all the gases are in the same container. That means that the volume would be the same for all the gases, right? So that's 1 liter. So that's the setup. So 3.5 times 0.0821 times 298, and then divide that by 28.02 times 1. Okay, so according to my calculation, this works out to be 3.06, and the units will be atmospheres, because again, we'll have some cancellations here. Grams will cancel out, moles will cancel out, Kelvin will cancel out, liters will cancel out. So the only unit remaining will be the atmospheric unit. And that's how we calculate the pressure of nitrogen. And basically it's the same calculation for all the other gases. So let's do so for the hydrogen. The mass of the hydrogen, yes ma'am.
Just a quick question, what was the difference between capital and the lowercase?
Okay, good question, actually. The lowercase m is the mass in grams, and the capital or uppercase M is molar mass, right? So yeah, that's a very important distinction that you need to remember. Lowercase m is mass in grams, uppercase M is molar mass. All right. Okay, so the mass of the hydrogen is 2.15 grams multiplied by 0.081 liters atmospheres over mole Kelvin times the temperature, which is 298 Kelvin, all divided by the molar mass of hydrogen, which is 2 times 1.008, so that would be 2.016 grams per mole, multiplied by 1.00 liter. So let's see what that gives. 2.15 times 0.0821 times 298, and then divide by 3.016. And according to my calculation, again rounded out to 3 sig figs, that is going to be equal to 26.1 atmospheres. And that's how that is done. All right, for hydrogen. Okay, any question about that one? Since I'm going to need space, I'm just going to erase the calculation. In fact, let me do this. Let me just erase this part right here, because now we're going to do the same calculation for ammonia. So this is NH3. I'm only going to erase some of these terms here. I'm going to erase the mass here because the mass is going to be different. And I'm going to erase the molar mass here and fill them in. So in the case of ammonia, the mass according to the question is 5.27 grams. And the molar mass now would be nitrogen, which is 14.01. 4.01 plus 3 times 1.008. So 17.03 grams per mole would be the molar mass, right? So that's basically it. Of course, I need to erase this here and replace it with the answer for that calculation. So let's do the calculation. 5.27 times 0.0821 times 298, and then I'll divide that by 17.03. And according to my calculation, this work out to be equal to 7.57 atmospheres. All right, and that's it, because the question is just asking for us to calculate the partial pressure of each component. All right, okay. And if the question had asked to calculate the total pressure, right? How would you do that? Just, I'm just throwing that question in. How would you calculate the total pressure?
We just add them all together.
You just add up all the pressures that you just calculated. And that would be the total pressure, all right? Okay, any questions about this? Any questions? Okay. There it is. Scroll down. Okay, now this one is an interesting question. It gives you 3 containers, containing gas. Well, it doesn't say whether or not the gases are the same or different. Doesn't matter in this case, right? Now it says container A has a volume of 1.23 decimeters cubed, and the pressure of the gas in that container is 3.24 atmospheres. Container B, it gives you the volume and its pressure. Container C, it gives you its volume and pressure. And then it says if all these gases were placed into a 4th container D, where the volume is 1.51 dm³, what is the pressure of that mixture in container D? All right. So my question to you is this: what laws do you think are involved in this question? And I'll say that there are 2 laws. So that's a little hint right there. There are 2 laws that will come into play when it comes to solving this problem. So what laws would you think of? What 2 laws would you think of? Let me give you a little hint. So one of the laws involves what should I put? One of the laws involves what happens to the pressure when the volume changes. Which law is that? Yes, ma'am. Boyle's law, exactly, right? And then there's another law which deals with mixtures. Dalton's law, exactly. Okay, very good. So, how do we tackle this? Okay, so basically, you have to treat each gas separately in terms of the changes in pressure and volume, right? So let's deal with gas A. The initial volume, so for A, let me go for, I'm just going to say gas A. Even though they may be the same gas, but it doesn't matter. For gas A, this is the initial volume. This is the initial pressure. And because that gas is placed into container B, that will be the final volume. All right? So, how do we calculate the final pressure for gas A? P1 V1 over V2. Okay. So P1 will be equal to what? 3.24 atmospheres. And what is V1 for gas A?
1.23 decimeters.
1.23 decimeters cubed divided by V2. What's the final volume? 1.51 dm³, exactly. So let's work this out. 3.24 times 1.23, and then divided by 1.51. And according to my calculation, when rounded up to 3 sig figs, the final pressure is 2.64. 2.64 atmospheres, right? So that's for gas A. For gas B, same equation. So P2 would be equal to what in the case of gas B? What is P1 in the case of gas B? .82 atmospheres. What is V1 for gas B?
0.94.
0.93 atmosphere, not atmosphere, I'm sorry, dm³. And then what is V2? 1.51 dm³. Right? So let's see what this gives. 2.82 times 0.93 and then divided by 1.51. So this would have to be rounded out to two sig figs, so that would be 1.7 atmospheres. Right? Okay, so that's for gas B. So now we get to gas C. For gas C, again, we're calculating the final pressure. So what would be the initial pressure, P1, for gas C? 1.21 atmospheres multiplied by, what's the volume? V1 for gas C. 1.42 decimeters cubed, and then divide that by the final volume, which again is 1.51 dm cubed. Let's see what that gives. So 1.21 times 1.42, and then divided by 1.51. So according to my calculation, this works out to be equal to 1.14 atmospheres. Okay, so we have calculated the individual pressures of the gas when they're all squeezed into container D. So therefore, to find the total pressure, how do we do that? We add them up, right? So we add 2.64 atmospheres plus 1.7 atmospheres plus 1.14 atmospheres. Let's see what that gives. 2.64 plus 1.7 plus 1.14. And when we're adding a round off to the lowest number of decimal places, which would be one decimal place. So according to my calculation, this works out to be equal to 5.5 atmospheres. And that would be the answer for that question, all right? Any questions about this one? Any questions? Questions? Okay, so we can see this is a combination. In solving this problem, we have to combine the Boyle's law, which we did first to calculate the individual pressures, and then we have to use what's his name? I forgot the law. Dalton's law to figure out the total pressure. All right. Okay. Let me clear this and scroll down. Okay. Now this one is another one which, again, you have to use both laws. It says a mixture of gases is made by connecting a 7.50 liter flask containing nitrogen at 2.0 atmospheres to a 13.0 liter flask containing hydrogen at 1.0 atmospheres. So the first question is, what is the final volume of each flask? Now, what I think would help a whole lot is if we draw a diagram to represent what we have here, right? So we have two flasks, right? We have this flask here, which contains, and please forgive my poor artistic skills, I'm not gifted when it comes to drawing, right? So this flask here contains nitrogen, and it has a volume of 7.50 liters, and the pressure is 2.00 atmospheres, right? So it's connected to another flask, which, let's say you have something separating here, like a tap. This flask will contain hydrogen, and the volume is 13.0 liters, and the pressure is 1.00 atmosphere. All right, so this is the situation. So so basically, let's say you open this up, right? So let me erase this here. So let's say you open this up so that the hydrogen and nitrogen can freely mix together in the entire apparatus, right? So the first question is asking for the final volume of each gas. So what do you think the final volume is? After both gases fill the entire apparatus. I'm sorry? Okay, and you got that by doing what? Exactly, you add the 7.50 liters to the 13.0, so the final volume would be 7.50 liters plus 13.0 liters, and that would give you 20.5 liters, all right? So that's the final volume upon mixing, all right? Okay, so, let me scroll down here, because the next question is asking, what is the partial pressure of each gas? And I think what the question is asking for is the partial pressure of each gas upon mixing. Because they gave us the pressures of the gases before mixing, right? So how do you think you'd solve this particular problem? Let's start off with the nitrogen, you know. How will you find the partial pressure of nitrogen after mixing? Anybody?
Basically, P1, B1, B2, B2.
Exactly. So in the case of nitrogen, what they're asking for is P2, right? So P2 equal to P1, V1 over N1. I'm sorry, over V2, I don't know, V2, right? So in this particular case, before mixing, P1 is for nitrogen 2.00 atmospheres, and V1 before mixing is 7.50 liters. And then after mixing, V2, the final volume is 20.5 liters. So let's see what that gives. 2 times 7.5 divided by 20.5. And according to my calculation, rounded up to, oh, this can't be right. Wait a second. 2 times 7.5 divided by 20.5. Okay, that's more like it. So I got, and please correct me if I'm wrong, but this is what I got. I got 0.732, and that would be atmospheres, right? So that's the pressure of the nitrogen after mixing. What about the pressure of the hydrogen after mixing? That would be equal to what?
You use the values,
Okay, so what are the numbers I need to write on? 1.00 atmospheres times
13.08.
13.0 liters divided by 20.5 liters, exactly. Okay, so let's see what I get. 1 times 13 and then divided by 20.5. And according to my calculation, that gives 0.634 atmospheres. All right. So that would be what the partial pressure of each gas is going to be. All right. Okay, any questions about this? Any questions? Any questions? And I think there is a C part. Oh, what's the total pressure? Well, that's easy, right? How do we get the total pressure? You just add the two pressures of the nitrogen and hydrogen. So total pressure will be equal to 0.732 atmospheres plus 0.634 atmospheres. And let's see what that gives. 0.732 plus 0.634. And I got, now when you're adding, you have to round off to the lowest number of decimal places. So when I did that, I got 1.366. And the units would be atmospheres. Whoops. What did I do? All right. And that's how that is done. Any questions about this one? Any questions? Any questions out there in Zoom? let me clear this. And scroll down. Let's see what's next.
Yeah.
Oh, now this one is dealing with collecting a gas over water. Right? What's the equation that we derived when it comes to that type of situation? Can anybody tell me? When you're collecting a gas over water. There's an equation that we derived which is applicable to that situation. Yes, ma'am.
Minus
Okay,
barometric pressure.
the total pressure minus the vapor pressure of the water. But there's another term that we use here instead of total pressure, which is equal to the total pressure in the situation. What's that term?
Barometric.
I'm sorry?
The barometric pressure.
Barometric pressure, exactly, that's what I was looking for. Right? Okay, so in order to calculate the pressure of the oxygen in this particular situation, we need the barometric pressure and we need the vapor pressure of water. Actually, what the question is asking for is the grams of oxygen, right? But before we get to that stage, we need to calculate the pressure of the oxygen. Now, the barometric pressure is given as 19 point, no, I'm sorry, that's the vapor pressure. 762 millimeters mercury, right? 762 millimeters mercury is the barometric pressure. While the vapor pressure of water is 19.8 millimeters mercury, all right? So now we can calculate the pressure of the oxygen, which is 762 minus 19.8. And according to my calculation, that works out to be 742 millimeters mercury. All right. Now, how do we get the mass of oxygen, right? Well, if you recall, there's an equation that we met earlier that is molar mass is equal to mRT over PV, right? We can rearrange this to get m, lowercase m. Remember, we talked about the difference between lowercase m and uppercase m, right? The question is asking for the mass in grams, so that's lowercase m, right? Lowercase m would therefore be equal to uppercase M PV over RT, right? Now, we know what P is. That's the pressure of the oxygen. The molar mass we can get because we have the formula for oxygen. The volume is 193 mils. The temperature is 22 degrees Celsius. So we have everything we need to calculate the mass of the oxygen. So the molar mass of the oxygen is 32.00 grams per mole multiplied by the pressure. What's the pressure? 742 millimeters mercury, but we have to convert that to atmospheres. 1 atmosphere over 760 millimeters mercury, and then we multiply by the volume, which is 193 mils, which we have to convert to liters, so that will be 0.193 liters. And then we divide that by R, which is always 0.0821 liters atmospheres over mole Kelvin. And then we multiply by the temperature, which is 22 degrees, which we have to convert to Kelvin. So that's 295 Kelvin. 295 Kelvin. And that's it. So in terms of the cancellation of units, the liters will cancel out here and here. The moles will cancel out here and here. The Kelvin will cancel out here and here. Atmospheres will cancel out here and here. Millimeters mercury will cancel out here and here. So basically you'll be left with the units of grams, which is what the question is asking for. So let's do the number crunching. 32 times 742 times 0.193 divided by 0.0821 times 295. So according to my calculation, let me do this again. Get it some 2 times 742 times 0.153 divided by 0.01 times 5. Okay, that was wrong. What did I do wrong? I forgot to divide by 760. That looks more, makes sense, more for reasonable answer. So the answer I got will be 0.249 grams. Yes, 0.249 grams, okay. I got an answer before as 189 grams. That wouldn't make any sense for mass of oxygen. All right. Okay, so any questions about this? Any questions about this particular problem? Number 11. Any questions? Okay, moving on. Let me clear this first. Let's go down. Okay, this one is a gas stoichiometric type problem. It gives you the balance equation. And it's asking how many liters of ammonia at 850 degrees Celsius and 5.0 atmospheres are required to react with 1.00 moles of oxygen. Okay, so let me hear some ideas about how you tackle this problem. They gave you the balance equation. They gave you the temperature of ammonia. They gave you the pressure of ammonia. And they gave you the moles of oxygen. Right? So what's the first step you would take in solving this particular problem?
What's the mole ratio of NH3 to oxygen to figure out how to use NH3?
Okay, so you're saying use the mole ratio between the NH3 and the oxygen to do what?
Find out how much NH3 are in moles.
Okay, very good. All right, so I agree with you. So basically you're going to start off with 1.00 moles, excuse me, of oxygen. And as she correctly said, you're going to use the mole ratio between the ammonia and the oxygen to find the moles of ammonia. So it's a 4 to 5 mole ratio. You're going to put 4 moles of ammonia above as a numerator and 5 moles of oxygen below, 5 moles of O2 below as the denominator, right? So according to this now, this will give you 0.800 moles of ammonia. Okay, so that's a very important first step, and that's correct. So what's the next step? Remember now, the aim is to get what? Volume. Okay, so now that we have the moles of ammonia, how would you get the volume of ammonia? Or what formula? Let me ask you this. What formula would you use to calculate the volume?
Use PV RT.
Okay, very good. So you use PV is equal to nRT. They gave you the pressure, they gave you the number, well, you determine the number of moles, you know what R is, and they gave you the temperature. So basically, we have to solve for V. So V would be equal to nRT over P. N is equal to what we just calculated here, which is 0.800 moles, times R, which is 0.0821 liters atmospheres over mole Kelvin. Times T. What is T? 850 plus 273. So according to my calculation, that would be 1123 or 1123 Kelvin. And then we divide all of that by P, which is 5.00 atmospheres. Okay, so let's do the number crunching. 0.8 times 0.0821 times 1123, and then I'm going to divide that by 5, And according to my calculation, again, please correct me if I'm wrong, but I got rounded off to 3 sig figs, 14.8, and the units here would be liters because kelvins will cancel out, the atmospheres will cancel out, the moles will cancel out. So the only unit remaining would be the liters unit. And that's how that is done, all right? Any questions about this one? Any questions? Any questions? Any questions? All right, I take it you're finished with writing this down, right? All right, so let me clear it. And let me move on to the B part. Now, the B part is based on the same equation, right? And the question is asking how many moles of water can be prepared by using 450 liters of ammonia at a pressure of 5.00 atmospheres and a temperature of 295 Kelvin. So let me hear your ideas about this one. How would you tackle this particular problem? They gave you, what did they give you? They gave you the volume of ammonia. They gave you the pressure of ammonia. They gave you the temperature of ammonia. And they're asking for the moles of water, right? So what's the first step in this process? Yes, ma'am.
This equation, rearrange it, solve.
Moles of ammonia, right? So again, the PV is equal to nRT equation is what you would use, but as she correctly said, you're going to find N. So N will be equal to, when you rearrange this, PV over RT. So P is 5.00 atmospheres times V, which is 450 liters, divided by R, which is 0.0821 liters atmospheres over mole Kelvin, multiplied by the temperature, which is 295 Kelvin. Right? So let's see what this gives. Divided by 0.081. Okay, so according to my calculation, this works out to be, okay, how many sig figs here? 2 sig figs. So this works out to be 93 moles. So this would be the moles of ammonia. All right, so what's the next step? Now remember, the question is asking for what? The moles of water, right? What you have just calculated here is the moles of ammonia. So how would we get from 93 moles of ammonia to moles of water? What's the conversion factor you would use to go from moles of ammonia to moles of water?
Take what we had from the previous.
I'm sorry?
Will we just take what we had from the previous one or itself, so for every, 4 ammonia we have, 5 with the,
For every 4
or,
moles of ammonia, there'll be 5 moles of oxygen. Okay, good. So what would go up top and what would go below here?
below would be the 4,
4 moles of NH3, and what would go above?
5
5 moles of O2. Very good.
would be,
Oh, my bad. Good pickup. He's absolutely right. We're not calculating oxygen. We're calculating the moles of water. So that will be 6 moles of H2O. Thank you very much for that correction, sir. So let's see here. 93 times 6 divided by 4. So again, round off 2 sig figs. So this gives you 2 sig figs. So that's 140 moles of H2O. All right. So that's how that is done. All right. Okay. Any questions about this one? Any questions? Any questions? Any questions? Alrighty. Let's continue. Maybe we can squeeze in one last one. Oh, the grades first. Yeah, squeeze in one last one before we get to this class. Okay, oh, so this one now has to do with effusion, and I don't remember if I told you guys this. In some textbooks, and you're gonna see that here in some of these questions, the terms diffusion and effusion are confused, right? I made a distinction in class, right? So you may want to read up on that, right? But just to let you know that, you know, if you're studying and you come across, in some textbooks, Graham's law being applied to diffusion, that's a very common error that is made in, chemical literature. But keep in mind that those are two different phenomena, right? Diffusion and diffusion. And, Graham's law only applies to effusion, not diffusion, all right? So this question says, you have, an experiment where an unknown gas diffuses 1.5 times longer compared to oxygen. So the question is asking for you to find the molar mass of the gas, all right? Now, let's remind ourselves of what Graham's law of effusion says. It says that the rate of effusion of a gas is equal to the square, not equal to, but proportional to the square root of 1 over the molar mass of that gas, all right? Now, in this particular case, we don't know what the gas is. It's an unknown gas, and we're comparing it to oxygen, which is a known gas. So we can write down an expression for the rate of effusion of that unknown gas divided by the rate of effusion of oxygen, and that would be equal to the square root of the molar mass of oxygen divided by the molar mass of that unknown gas, right? So based on the direct application of Graham's law of diffusion, we can write down that expression. Now, here's where things are interesting. The question says that the unknown gas diffuses 1.5 times longer, right? So we're not talking about rate of effusion. We're talking about how long the gas takes to diffuse, right? And I remember saying in class that I think we did 1 or 2 examples. No, I think it's 1 example where the question was giving you information or something involving the time of effusion. And if you remember, I said that there's an inverse relationship between rate and time, right? So if something takes a short time, it has a faster rate. If something takes a longer time, then the rate is slow. So we can include that part of the discussion here, where the time of effusion of oxygen divided by the time of effusion of the gas will be equal to what we have over here, right? Now, the question says that the time of effusion of the gas is 1.5 times that of oxygen. So we can say that the time of effusion of the gas divided by 1.5 times, I'm sorry, time of effusion of oxygen divided by 1.5 times the time of effusion of oxygen, because this here would be equal to this. So we can put that there, and then this would cancel out. And then we can put here the molar mass of oxygen, which would be 32. In fact, you know what? Let me, I'm sorry. I'm making things a bit more complicated than it should be. Let me do some rearrangement first, and then we put the numbers in. So, the aim of this is to determine this, right? So, first question I have to ask you is, how would I get rid of the square root sign? Square both sides, right? So if you square both sides, you're gonna end up with MO2 over Mg is equal to TO2 over TG squared, right? And then now, to find the molar mass of the gas, that would be equal to MO2 multiplied by time of effusion of the gas divided by time of effusion of oxygen squared, all right? So this is the expression we're going to use now to calculate the molar mass of the gas. So all we have to do is plug the numbers in. For the molar mass of oxygen, that would be 32.00 grams per mole. And then I have to multiply by Tg over TO2. But guess what? The question says that the time of effusion, the time of effusion of the gas is 1.5 multiplied by times of fusion of oxygen, which means that time of infusion of gas divided by TO2 will be equal to 1.5. So this here can be replaced by 1.5. So this is here and put 1.5 here. 1.5 squared. So let's see what that gives. 32 times 1.5 squared. And according to my calculation, this works out to be equal to 72 grams per mole. And that's how that is done. All right? Okay, so I have to stop there. What I would suggest to do is that you try the other questions. How many questions are there? Yeah. 14, you have 15, you have 16, you have 17, you have 18. Okay, so try those questions. If you have any problems, come and see me. Okay, so I take it you all know that there will be no class on Thursday, right? So, I want to take this opportunity to let you know that according to the syllabus, your next test will be, next week, right? Hold on, wait a minute. Today's what?
7.
So, oh, okay, good. I have a meeting on the 17th. Okay, so, your next test will be on the 16th. I'm desperately trying to, grade, oh, where is it? So your next test will be based on chapters 3, 4, and this chapter 5, all right? So, I'm desperately trying to get back to you. I've graded test numbers, assignment number 3 already. I'm going to see if I can get it back to you, graded, and graded work back to you today. I have to grade assignment number 4. I'm going to try to get that back to you as soon as possible. And then this assignment now, I'm going to set a deadline. Today's what? Today is Tuesday. Okay, so I'm going to set a deadline for submission of this assignment as Friday. And then I'll grade it over the weekend and get it back to you as well, so that you'll have it, all those assignments to review for your upcoming test, all right? So that's basically what's gonna happen next week, so please be prepared for that test on chapter 16, on October 16, which will be based on chapters 3, 4, and 5, all right? Okay, so that's it about our announcement, so I'll see you guys next week, Tuesday. And for you guys out there in Zoom, I'm signing off now.